Okay, in this lecture we're going to talk about free energy, which we defined earlier, but those equations were limited to working at standard conditions. So here we're going to look at equations describing some non-standard conditions. Okay, let's remind ourselves what standard conditions are, right? Standard conditions under which we measure thermodynamic quantities are a temperature of 25 degrees Celsius, or 298 Kelvin, right? Any solids or liquids participating in the reaction are taken to be pure. Any gases have a pressure of 1 atmosphere, and any solutes have a concentration of 1 molar, right? So if we set up, right, a reaction, so if we have A plus B makes C and D, and we make an equilibrium constant, or actually probably more appropriate would be Q, since we don't know that we're at equilibrium, right? Whether, right, we've got our equilibrium constant, or our expression for Q, right? Whether we've got solutes, whether we've got gases, or whether we've got pure liquids, and remember their activity is 1, everything in this equation becomes 1. Right? So we're really restricting ourselves to the situation where Q is 1, right? And so if delta G0 is negative, that is, if it's less than 1, then that tells us the reaction is going to move toward that direction for Q to approach the equilibrium constant, right? The reaction will go forward, and so that tells us the equilibrium constant will end up being greater than 1. If our delta G0 is positive, right, that means the reaction will have to go back that direction to reach equilibrium, right? It's unfavorable in the forward direction, which means it's favorable in the reverse direction. And that tells us, right, in order for Q to approach the equilibrium constant, which it means that the equilibrium constant will be less than 1, right? So delta G0 tells us something about the direction that the reaction has to move, again, starting under standard conditions, to move toward equilibrium, which connects delta G0 with the equilibrium constant. Right, so here's the equation that expresses that relationship, right? Delta G0 is equal to negative RT times the natural log of the equilibrium constant for the reaction that we're dealing with, right? And so if we look at a diagram like this, right, we've got a period over here where delta G0 is negative, right? Remember that here Q is equal to 1. And if delta G0 is negative, the reaction will move to the right to move toward equilibrium. And so that means our equilibrium constant must be greater than 1 for that reaction, right? And similarly, right, if our delta G0 is positive, right, that means the reaction is going to tend to move back to the left. That means we have too many products, right? So if Q equals 1 and we have to move to the left to reach equilibrium, then the equilibrium constant is less than 1, right? Now, remember when we did the problem before, we said the transition between is that delta G equals 0, right? And so how do we deal with that question, right? So at this point, we have figured out that when delta G equals 0, the system is at equilibrium, right? So if we rearrange this equation just a little bit, right, we can get that 0 is equal to delta G0 plus RT times the natural log of the equilibrium constant, right? That is, right, when Q is equal to the equilibrium constant, this term offsets that term and makes delta G 0, right? But now we can, go back and use this, right? If we're not at equilibrium, then the delta G is equal to the delta G0 plus RT times the natural log of Q, right? And so we get an expression that will tell us the delta G for a condition other than equilibrium, as long as we know the delta G0 for that process. And so this becomes a very important equation in thermodynamics, right? And one that we will do a lot with.